All right, let's dive right in. We're going to follow a molecule on a really critical journey through the body. Now, on one hand, it's just a simple waste product, but on the other, it's a potent neurotoxin if it's not handled just right. This is the story of unconjugated bilirubin.
So where does this stuff even come from? Well, it all starts when your old red blood cells get broken down. Their hemoglobin releases its core component, which is called heme. From there, it's a super quick two-step chemical reaction. First, an enzyme called heme oxygenase turns heme into a green pigment called biliverdin. Then, almost immediately, another enzyme, biliverdin reductase, converts that into unconjugated bilirubin. And this is the raw, unprocessed form, and this is exactly where the trouble begins.
And that brings us to the central problem here. See, unconjugated bilirubin isn't just waste. Its chemical nature is what makes it so dangerous. It's lipid-soluble, or you could say fat-soluble, and that one single property is the root cause of all its toxicity.
Okay, think about this for a second. Water-soluble molecules? They're pretty easy for our body to handle. You know, they dissolve in blood, they get flushed out by the kidneys, no problem. But lipid-soluble molecules? They're sneaky. They can slip right through the fatty membranes that make up our cells. And for bilirubin, this means it basically has an all-access pass to get into places it should never, ever be, especially the brain, where it acts as a straight-up neurotoxin.
So the body's got this major challenge on its hands. It's just made this toxic, lipid-soluble molecule, maybe in the spleen or the bone marrow, and it needs to get it all the way to the liver to be detoxified. So how does it do that? How do you move this stuff through the bloodstream without it leaking out and damaging sensitive tissues along the way? Well, the solution is just incredibly elegant. The body gives this toxic passenger its own personal bodyguard to make sure it stays exactly where it's supposed to be, in the bloodstream. And this bodyguard happens to be one of the most important proteins in our entire body, albumin. So by binding super tightly to bilirubin, albumin does two absolutely critical things. First, it completely neutralizes the threat. It physically blocks the bilirubin from crossing the blood-brain barrier, which prevents that neurotoxicity we were talking about. And second, this new bilirubin-albumin complex is now way, way too big to get filtered out by the kidneys. So it's effectively trapped in the bloodstream, which guarantees it's going to make it all the way to its final destination, the liver. And what's so cool is that this biochemistry perfectly explains a classic clinical sign. When this whole system gets overwhelmed and bilirubin levels start to rise, it causes jaundice, that yellowing in the tissues. But here's the thing. It doesn't just show up everywhere at once. There's a very specific place it shows up first. And this brings us to a really important clinical question. We've all heard that yellow eyes are a sign of liver problems, right? But why the eyes specifically? Why not your hands or your face? Well, the answer comes down to a very specific chemical attraction. The entire reason boils down to a single protein that has this unique relationship with bilirubin, and that protein is called elastin. It turns out the sclera, that's the white part of our eyes, is absolutely packed with elastin. And for whatever chemical reason, bilirubin has an incredibly high affinity for it. It's like a magnet. It literally sticks to the elastin in the eyes first, way before it's built up enough to be noticeable anywhere else. And that's exactly why yellowing of the eyes, or scleral icterus, is the earliest and most reliable sign that something's wrong. Okay, let's put everything we've just learned about solubility and transport together to solve one final diagnostic puzzle. The question sounds simple, but the answer is incredibly precise. Even if a patient has sky-high levels of unconjugated bilirubin in their blood, why will you never, and I mean never, find it in their urine? The answer comes down to two simple failures at the kidney. It fails two separate tests. First up, solubility. It's lipid soluble, remember? So it just can't dissolve in our water-based urine. It's like trying to dissolve oil in water. And second, transport. It's latched onto that massive albumin protein, making the whole complex physically too big to get squeezed through the kidney's filters. So it's insoluble and it's too big. That's why its presence in urine is a flat-out impossibility. So that leaves us with this final thought. We've seen this incredible system where albumin acts as the essential bodyguard for this toxic little passenger. But what happens when that bodyguard is weak, or there just aren't enough of them, or they're just completely overwhelmed? That's when the whole system breaks down and the true toxic power of bilirubin is finally unleashed on the body.